G'day students. So here we have a question that we've used in the quiz. It's a quintessential 3/4 rule problem. So quintessential that it's actually in your Year 11 textbook. I wrote a very similar question to use it to illustrate the 3/4 rule. Now the key thing about this 3/4 rule problem is we have a person lifting some sort of post, but the post is being held in position as shown. So the system's in equilibrium. Now, the 3/4 rule tells us that a body will remain, if a body's in equilibrium, it will remain in equilibrium if it has 3 forces acting on it, and those 3 forces must be concurrent or parallel. Now, quite clearly, this is not a system of parallel forces. It's a system of concurrent forces if we have 3 forces indeed. So first what we need to do is we need to find out where the point of concurrency is. So we're going to project up here and extend the line of action of this weight force until it intersects with the tension force there. Now once we do that, that finds us our point of concurrency. Now, where's the third force? Well, we have to think about this logically. What force is putting this in equilibrium? We have a weight force that's going down like that. We've got an angled force here, which is the tension in the rope, which is both going to the left and has also got a downwards component as well. So we have no upwards force at the moment to balance this situation, and we have no force going to the right. So there must be another force, a reaction somewhere. Now logically, I hope you can all look at this and think, well, obviously the reaction has to occur at the ground. If there wasn't a vertical component here, then it would sink into the ground. If there wasn't a reaction here at that step, it would slide back towards the person. So there must be some sort of, if we combine those two components, we're going to get a reaction. What is the direction of that reaction? Well, that's unknown, except for the fact that we know that with a 3/4 rule, then it's either, the forces are either parallel or concurrent. So quite clearly in this situation, they're concurrent. So there's our point of concurrency, there's our point of application. So our reaction is down here like that. We can extend the line of action to show that, but there's my reaction there like so. So that allows me to find this reaction. I can measure it using my protractor and find that angle there, theta, to the horizontal. I know that this is at 30 degrees to the pole, which means it must be at 15 degrees to the horizontal because alternate angles are equal. And so I've got a vertical force with a known magnitude, 200 newtons, and I have these two forces where I now know their direction, so it's possible for me to solve that. So let's have a look how I'm going to go about doing that. So if I now look at the graphical solution, what I have is, like I did with the texter, I've extended the line of action here like so, and what I've done is so let's have a look at what I've done here with the graphical solution. So let's have a look at what I've done here with the graphical solution. So there's my line of action that I have. There's the line of action of the vertical. There's the point of concurrency. I've extended this one down to scale to represent 200 newtons. I've extended this line that I drew. And then what I've done is I've taken this line at 15 degrees below the horizontal and I've drawn it off the end of the known distance until it intersects there. When I measure that, I find that to be 57.5 millimetres, and that means it's approximately equal to 144 newtons. So when I go back to my question here, what's the closest answer? 141 is going to be the closest answer to 144. Now, we can also do this problem analytically. Now, I tend to prefer doing it via the 3/4 rule, and in many situations, these questions won't tell you a length, so you have no choice but to do it via the 3/4 rule. But in this case, we're told that the pole is 4 metres long. Now we're assuming the weight is distributed uniformly, so therefore the mass is distributed uniformly, so our weight force is in the middle, so it's 2 metres there. So what that means is that we know that we'll be able to work out what this distance here, the perpendicular distance, is from here to here, and we'll be able to work that out up there. Because if we're going to find the tension in the rope T, we need to take moments somewhere that's going to eliminate an unknown. And the unknown is this reaction here, which we already know exists. So, how do we go about doing that? Well, if I go back to my solutions here, let's look at the analytical solution. So there's my post, there's the ground where I'm going to take moments. Now remember, there is a reaction there that is unknown. We found it using the 3/4 rule, but we're considering approaching this as an analytical solution, so we don't actually know what it is. But I do know some things. I know that that's 200 newtons. I know that that 200 newton force is 2 metres away, so that distance there is 2 cos 45 degrees, because the post is at 45 degrees. I know this angle is 30 degrees, and that must be 15 degrees, because alternate angles are equal, so that's what that has to be. That's why this is T cos 15, that's what the S is doing there, and T sine 15 degrees. Now, this is 4 metres long, so the perpendicular distance from there to there is going to be 4 cos 45 degrees, and the perpendicular distance from there up to there is going to be 4 sine 45 degrees. So, I'm going to sum the moments about G. I've got 200 times by 2 cos 45 plus T sine 15 times 4 cos 45. So both of those forces are going clockwise, both those moments are going clockwise, so they're positive. Minus T cos 45 times by 4 sine 45. So I end up with that number, 2 values for T there. They add together to make 2T, and my final answer is 141.4 newtons. Now in this situation, I don't think the analytical version is that tricky. It's pretty straightforward. You're summing moments about a point. Where I think the 3/4 rule comes way out in front is if you were asked to find this force as well. So when you're just asked to find T, moments isn't too bad. If you're asked to find the reaction at the ground as well, you would now have to sum forces vertical, sum forces horizontal, and then add those two together vectorially to find both the magnitude of the reaction at G and the angle. So in that case, I think it would be much better to use the 3/4 rule. But if we're just finding T, then moments is quite acceptable in this situation.